Today on Xeno I have some interesting lasers of which I am going to be showing you in this video. So these were sent to me by a fellow friend and laser enthusiast. In fact, I am now the fourth laser enthusiast technician to try to attempt any kind of meaningful repair on them successfully. Two of these technicians are my superiors. So this could be a really interesting video to stick around for. So these are intercavity doubled vertical cavity surface emitting lasers, and I haven't really seen anything like these before. Let's go over what my friend sent. So here's what these look like. These are Protera units. I believe they're made by NovaLux. I saw that on one of the ribbon cables on the inside. This laser is 532 nanometers, and it looks like it's in pretty good condition. Doesn't look like any parts are missing, so hopefully it's something simple, like an alignment issue. So these are pumped by vertical cavity surface emitting lasers, not normal laser diodes like the double heterostructural ones. I'll show you more of that later on in the video. That sits right there, acts like a pump diode. This one is 1064 nanometers, so about 1 micron or so. Inside here is a second harmonic optic nonlinear crystal, which doubles that into 532 nanometers. We have an output coupler optic here, which forms the resonator, an optical pickup, and then a collimating lens. This is the only 532 nanometer unit he sent over. The rest of the lasers are 488 nanometers. So let's take a look at some of those. So here's one. You can see the same block right here, copper block. That copper block sits on a thermoelectric cooler, TEC. And there's a couple of NTC thermistors on the side over here, the output coupler. So this unit looks pretty savable. Maybe we can get some laser light out of this one. Here's another unit he sent over. The TEC looks like it's pretty good. The output coupler is missing, but you can kind of see inside what's going on. So there's another little thermoelectric cooler right here, and the nonlinear crystal sits on top of that. So this outside copper block here is actually cooled. That keeps the pump diode cool, and the nonlinear crystal there for doing the second harmonic generation actually needs to be warmed in order for it to work properly. So maybe clean that up. Maybe that one could be saved. We have a full another resonator here, missing some screws. That's pretty rough. The wires are torn off. I don't know if that's fixable. We'll see. But it has a spare output coupler. Another output coupler. Oh, these are slightly different colors. Interesting. Has more of a green, and this one is a kind of a pink. Another frame. Another resonator. So we got parts. I think there's another full resonator here somewhere. Yeah, here it is. So this one is just broken off the TEC, but otherwise looks like it's pretty much intact. So hopefully I can fix that one. So we may have 3 savable units. Maybe some of the repairs were attempted by people who I would consider my superior, as I said, so could be tricky. And some other miscellaneous parts, ribbon cables, some case parts, IR blocking window there, another lower frame section. These go on the back of the resonators like that. And there's another vertical cavity surface emitting laser here. Whoops. Let's take a good look at that. So unlike a regular laser diode, as a double heterostructural form factor construction, this actually emits from the top of that square. So that little black dot right in the center is where the light comes out. And from what I've been told, these don't actually laze until the output coupler is on. So that way stimulated emission can take place inside of that laser there. I want to see if I can collimate the output from one of these as is, and see if it works just as a regular laser without the output coupler. I've got questions. We're going to do some experiments. It's going to be a fun video. He also sent along a driver. Let's take a look at that. It looks like a pretty good driver. I tried to connect it up using a VGA cable. It didn't seem to like that. I don't know if I trust this driver. It looks like it would work just fine. So this transistor here, probably for driving the pump diode, takes about 500 milliamps, so half an amp. Got all the control circuitry up here for that. We have two TEC drivers right here. So one of these would cool the pump diode and that big block. The other one would warm the nonlinear crystal on the inside of the resonator. So I don't know if I'm going to use that driver. I don't trust it. So what I'm going to do is I'm going to use the driver that I made for a JDSU microgreen. So let's take a look at the JDSU microgreen. See what's inside of that. That way you understand why I want to use that driver. So here's a pump diode that needs to be cooled. Here's the resonator that needs to be warmed. There's two TECs, and they also use the same 10K NTC thermistors. So I'll be rewiring the driver that I made for that. Here's the driver. It's a pretty simple driver. So that should work for everything I need. Now these are touchy lasers from what I told, so the driver might not even be good enough. But we're going to find out probably the hard way. I also went through the laser heads and made myself a pinout of the back connector on the lasers, so I know how to wire up the driver. I'm not going to be doing that on camera. I have a whole video on how to find the wiring inside of a DPSS laser and track that all down in the video where I discuss how to connect a DPSS laser to a new driver. I'll link that below in the description. So yeah, that's the goal. In this video, I'm going to see how many of these laser units I can get running. Seems like a simple task. At this point, I have the driver I was using for the JDSU microgreen all rewired to go with the Protera lasers. I found out why the VGA cable wouldn't work, and that's because there are actually 3 internally connected pins on the center row, which would explain why the driver my friend sent over was drawing a whole bunch of current, wasn't working properly. So yeah, don't use VGA cables unless you're going to crack open the shell on the connector end and rewire that. Just something to be mindful. You'll probably also have to rewire it to the wires in the VGA cables. Not laser friendly. We'll just say that. Anyway, so this driver, as I said, handles a couple of things. You got the pump diode side for driving the pump diode current. That should be set to about 400 milliamps. We have the 2 thermoelectric controllers, one for cooling, one for warming, on the side that does the cooling, which is the larger one underneath that copper block. I have a 1 ohm resistor just to drop some of that current going to the thermoelectric cooler. And then I have this 10 ohm resistor right here. That's to drop current going to the warming TEC that warms the crystal inside of the resonator. So, that crystal, by the way, my friend says he thinks it's potassium niobate. So, but yeah, anyway, now that I got a driver, I can hopefully test out some things and see what works and what doesn't work. Let's go ahead and start with the green because that looked pretty promising. So get some life out of here. I guess they run at about 450 milliamps or so. So 400 milliamps should be just fine. Connect it up. See what we get. You know, I need more 532 nanometer in my life. Do I really need more 488 nanometer? Probably not. I have a lot of it. All right, I'm gonna need something I put as a target. Well, that might work. All right. Perfect. Look at that. All right. Power is the last thing. So, positive, negative. Quickly look over all my connections. Yeah, TEC. Yeah. It looks good. I don't see any major problems. More importantly, the pump diode looks like it's wired correctly. So hopefully that that doesn't become a disposable item. All right, current. Just to make sure we're where we're at, where we should be. Turn down the voltage knob. Power. All right, here we go. We got 5 volts. Oh, hey, we got an output. Wow. Okay, that's That's nice to see. Not very much, but we have output. Alright, let me see if I can mess around with the temperatures here. So on the driver, see if I can navigate this over. On the driver, there are two LEDs that'll blink. So I got this LED right here, and that's for the cooling, and I got this one right here, that's for the heating. The heating doesn't look like it's doing anything right now. Nope, it's stone cold. Looks like the cooling one is on. When they're operating properly, they should oscillate on and off pretty rhythmically. So, yeah. That one over is just getting warm. No, not at all. Oh, well, that's concerning. I wonder if that TEC works. I'm going to go ahead and throw a continuity meter across that, the continuity test, see what it says. Let's go ahead and see if we can get the crystal to turn on. Move that. Or the crystal TEC. Turn that up. And this one's going to have a lot to do with the brightness, too, of the laser, because depending on the temperature, the laser is going to be more efficient. Well, it looks like the crystal TEC is somewhat responding. Yeah, okay, so the crystal TEC is regulating properly. I still don't see any change on this one. Alright, so let's set it a little bit cooler, right on the edge. Alright, it should turn off. Should turn off real quick now. Not. Yeah, that TEC, it could be bad. My wiring could be wrong, but it could also be bad. Let's go and check that. Still messing around with the crystal temp a little bit more, see if we can get that dot any brighter, a bit more output. Does it say 5 milliwatt laser? Yeah, that's not 5 milliwatts. That's that does look like it says 488 milliamps. Oh, it'll go up to 450. Let's go up to 450. Oh, hey, they like that. You can get a more ideal crystal temp. Heck, we're getting some nice power of that. That's not that bad. I think this laser is savable. It needs a new TEC maybe. Let's go ahead and check that out real quick. Boy, that is a nice tight dot. Nice low bandwidth too. Okay, well, for the time being, bring this down back to 400 milliamps. I'm gonna go ahead and turn off the power supply. We're gonna go ahead and check the TEC. Off we go. I'm gonna need the meter for that. You know what? I'm gonna desolder the meter. And just, yeah, no, I'll keep that in line. I'll just jump for the time being. Let's go ahead and check that thermoelectric cooler. I'm excited. I'm excited. So far, we're getting good news. Megohms. Ohms. That's not right. Yeah, I think that TEC is bad, and that's pretty common. I'd say, some of these TECs have definitely seen better days. So we'll mark that down on that laser. The TEC for the pump diode might be bad. All right, let's go ahead and move on to another laser head. See if we can get anything. This one looks to be the best candidate. I'm gonna go ahead and try this 488 nanometer one. See if we get any output. Oh, looks like we should though. Let's see. Yeah, it looks like it has everything. Maybe get lucky. Come on, give me that 488 nanometer light. You know you want to. You know you want to. We're not. That's cool too. Alright, what do we have here? Hey, the crystal is working. I see that light blinking. You mess with the pump diode temperature. Okay. So that came on. Let's see if the TEC for block is working. Are you getting cold? Oh, the resistor is getting warm. That's a good sign. It's getting very warm. All right, so that green light should start oscillating too. It already has. All right, all right. Very good. Carefully put that down. Go ahead and mess with the crystal temp. See if we get any output. I'm going to set the crystal temp down again. We'll wait till that stabilizes a little bit. Any 488 nanometer light? Go ahead and turn off the shop light. See if we can spot anything inside there. Nothing. Absolutely nothing. At least the LED works. Well, it's been a few days, but there has been measurable progress. So out of the 480 nanometer resonator cavities that I have still, I actually managed to get 3 of them to laze, even without temperature compensation. So they should come back to life pretty strong. This is the last one, and I can't get this one to laze at all. I tried some of the other pump diodes, and no lasing action. Gave all the optics a solvent wash, made sure they were pretty clean. Still, no lasing action. So there's got to be either a problem with the actual second harmonic crystal, which I think is potassium niobate, or there's a problem with one of those little turning optics on the inside of the resonator. Something's wrong. I would think that there would be photons coming out of here if it was working right. I don't think it's a crystal. I think it's something with those turning optics. By the way, the other resonators that I did get delays, I did not replace the little turning optics inside of the resonator. I'm probably going to make my own. We'll see. They may not even need them, and I'll explain to you exactly what those are as soon as I get this apart. Well, let's take a look at the inside of the resonator. Now, on the inside of this unit, you'll notice that there are these two little metal posts that come up. So here's one that comes in from the top, and then behind there's one that comes in this way. And each one of those little posts, they have an optic on the inside, and that's a turning prism essentially. It's a piece of flat glass, but what it allows the person, so the people who make them, to do is to adjust where the output of the resonator is and where it lands on the output coupler. So, for example, if you want to make an adjustment as to where the beam goes on the output coupler, you can use these two little optics. By turning them, you can steer the beam ever so slightly and get the optimal position. So I have a feeling that there's something wrong in there. It just doesn't look right. We get a closer view in there. No, not really. It's like there's like some crack or something in there. I'm going to go ahead and see if I can get those turning mirrors out. Go ahead and grab a little flathead screwdriver. Carefully. See which one's the front one. Let's go take the front one out first. Oh, that moved actually relatively nicely. All right. And carefully pull out the turning optic. I don't want to rotate it completely. Just want to slide it on out. There it comes. And out we go. So that's one of the turning optics. Put that down. See what we have left. Boy, is that the crystal itself? That's weird. What is that? Go ahead and see if I can extract the other turning mirror here. The turning optic. That one comes out pretty easy too. Oh yeah. Looks like that crystal is broken. I'll take off the pump. Oh yeah. That crystal is done. Well, another crystal I do have. I can get that one out. Well, that's going to be a tricky situation. I wonder if I can just push it out. It's already broken. So my biggest fear is breaking the TEC that everything sits on. Yeah, I think I'm gonna have to hit that with the heat gun very carefully. See if I can't heat that up. Break that crystal free. And if I do successfully, without destroying the TEC, come back and we'll put that other crystal in that I broke off earlier in this resonator and see if I can't get this to work. Well, that was a relatively painless process. One of success, so I can't complain. So it looks like I have the TEC in still working condition. Go ahead and test that with the continuity meter, but came off pretty painless. I took the heat gun, I heated up the copper crystal holder, and it kind of knocked it off. And then with a razor blade, box cutter blade, I went very carefully and scraped off the blue glue that held on the crystal. I took the aluminum ceramic substrate TEC plate off the bottom of this, prepped that, made sure it was all nice and clean too, gave everything an alcohol wash, and it looks pretty good. Well, all I need to do now is set this in here. Hopefully the alignment will be good. It's going to be a little alignment touchy, but hopefully it'll work. Oh, wish me luck on that. Time to mix up some epoxy. All right, now I need to use my eye to make sure that's aligned. So I'm going to move the camera. I'll come back when it's all set. But so far, looks promising. At this point, the epoxy should be fully set. So let's go over how everything looks. So I got the crystal glue on there. It looks pretty straight. Now, the angle of alignment on the second harmonic crystal is pretty critical. So even though it looks pretty good, it still has a high chance of not working, to be honest. But I do have my hopes. All right, I'm going to go ahead. I'm going to put this back together. We can see if it makes 488 nanometer laser light. I'm going to go ahead and first start with the pump laser diode. So put that on carefully. All right, it looks like the pump laser diode is now pretty centered. So I'm going to go ahead and tighten that up. All right, next I'm going to put on the output coupler. And I'm going to set this on loosely. I'm not going to put in the beam turning optics. I can actually adjust the resonator ever so slightly by moving the output coupler around, which is what I did with the other ones. And I want to find the most optimal position for the output coupler before I even go ahead and mess around with the turning optics. Alright, I'm going to check over all my connections real quick. They look okay. Good, good, good. Alright, let's fire up a laser, see if we can get any 480 nanometer light output. Drop the light. Hunting for a beam. Hunting for a beam. Nothing. Huh. I'm gonna play around with this, see if I can get some output. At this point, I've spent about a half an hour playing around with the position of the output coupler on the front of the resonator, and I still couldn't get it to lace, which is expected because the position of the crystal inside of these lasers is very fickle. However, there are two more pump diodes of which I decided to play around with. Of course, one was from the resonator of which I harvested the second harmonic generation crystal out of, and the second one was sent to me pretty loose in packaging. So I inspected both of them. One had a crack in the side. I tried the one from the resonator. It didn't work, but I did try the one with the crack in the side just for giggles. And of course, that's the one that works. I've got all the resonators I can get running. Effectively, I've run out of parts, so I couldn't build another resonator if I wanted to. So we'll consider this pretty much 100% success. Anyway, I'm going to go ahead and turn this light off and turn the power supply, bring up the voltage, and we can see some 488 nanometer photons. We'll be seeing a lot more of them in this video. Time for some fog. So I need to order thermoelectric coolers. Of course, these things are temperature stabilized. Temperature plays a huge role in how much output these have. But the fact that there's some output out of these resonators, oh, it's getting pretty bright. Oh, that's fantastic. Yeah, it looks like we're going to get decent output out of all these lasers. Significant time has passed, but look what the local postal ferry has delivered. That's right, it's a beautiful bouquet of 15 by 15 millimeter thermoelectric coolers. So let's get to fixing some of these Protera lasers. I'm going to start with the green laser. Pop the top off. Now the TEC is between this copper block and the laser base, and I frankly have no idea what needs to be unsoldered. So I think I'm just going to play the crank game. It's a very simple game. You just need a screwdriver, and you just need to apply some pressure until you hear crank. And that's how you play the crank game. So let's see what all needs to be desoldered and removed now. I'm going to start by removing the optical sensor. I'm going to see if there's a connector back here. Maybe that'll make taking it apart a little easier. The right tool will also help taking it apart a little easier. Well, that didn't seem to do anything. Oh, I accidentally ripped that off. That's okay. It's fixable. What is holding it in? Oh, okay. There's still just a little bit of glue on that TEC. That's what it was. Right. Well, now we got to get that TEC off. So my least favorite tool. Right. Well, that's going to be difficult. That's really glued on there. Most TECs are, but let's try a little trick that I learned while working on the Nova lasers, and that is to use a hardened steel pin to break the ceramic, and hopefully that'll help get the TEC off. Let's see, we can lock it kind of there. Fortunately, I can't really clamp onto this part. Put that there, maybe that'll sit nicely on that, and then got a hardened steel pin like this with a point. I'm going to try and break the ceramic using some percussive force. I don't necessarily like doing this, but it does seem to be one of the best ways to remove ceramic from lasers. So I don't really recommend this, but it works. That didn't go as smoothly as I thought it would. No such luck yet with removing that thermoelectric cooler, so I'm going to try an acetone soak and see if that loosens up the glue. Put that in position. Dump in some solvent. Let that soak for a little while. Good news, acetone does help with this particular glue, so I'm slowly but surely making progress. As you can see, I removed the resonator out of the laser, so it's a little easier to work on and I can clamp it down in the vise. Let's continue. Alright. Perfect. That'll fit in perfect. So I'm going to clean this all up and get ready to install the TEC. Alright, I now have 3 resonator assemblies that are fully ready for new TECs. I would have 4, but I gave one of the resonator assemblies to a good friend of mine to play around with, and one day we'll get more information on these laser units up on his website. But you know what? In the meantime, I have a crazy idea. Okay, so hear me out really quick. I just got a milling machine a couple of weeks ago, and I think it'd be really cool if I could see the inside of the resonator as it's running. And I'm certain you would like to see that too. So I'm going to try and very carefully remove the middle portion of the resonator copper block right here. Now mind you, the resonator crystal and the TEC, the crystal is on, is still inside. So I'm going to be very careful with this, and hopefully everything will work after this. Wish me luck. Hopefully we'll get some good video and pictures out of this attempt. I can't believe it took me this long to realize that I could just cut 2 slots. Alright, was that the right tool for the job? No idea. Did I do it right? Still don't know. Will it work? We'll find out. While my milling machine skills might need a little work, my glass ones are on point, and this looks fantastic. So, at this point, we can start rebuilding some of these Protera laser heads. So the first thing I'm going to do is actually glue the TECs on the bottom of the resonator. I'm going to show you a little trick for that. Got a little plastic bag right here, and I'm going to put the epoxy mix in here. It's a 5-to-1. I'm working with West Systems epoxy, the 105 and 205, and it's a really good epoxy. All right, now squeeze out as much of the air from the bag, and then now you can mix the epoxy just like this, and keep your hands relatively clean while doing it. That's done. I'm going to heat that up with the heat gun a little bit. It'll help kick it off a little quicker. And now flip that over. Usually the side that is marked with the numbers and letters and stuff, that's the cold side. I verified it with these. And in order to conveniently use your bag of epoxy, cut the corner off. And it saves you so much mess. Just like that. Now for the other 488 nanometer laser and the green.
And I already did the epoxying step on the bottom, so we can move forward a little quicker. Now, making sure that the surface of which you're epoxying to has been thoroughly cleaned is important. That'll help with the bond. You don't want any kind of oil on it, and that's already been cleaned with isopropyl alcohol. Now I'm going to drop this in, and I am going to just leave it like this for a while. Not for a while, but I'm going to leave it while I put this one in, and then I'll center both at the same time. Okay, and all I got to do now at this point is to carefully position them to where they're center in the right place, and then wait for the epoxy to set, and then we can move on with the other steps. Alright, at this point everything that needed to be epoxied together is now together, and to ensure that I had proper alignment and everything, here's what I did. I took these two brass standoffs and I mounted them in my optical breadboard, and I used this piece of perforated steel with a little styrofoam block, which gave me some downwards clamping force as the epoxy set, just to make sure that TEC laid flat. Let's take this off. And I also used these little plastic shims just to make sure that the module was centered. And take and dump those out. Alright, and hopefully we'll have a couple of lasers nearly fully put together in about an hour. Okay, so I already installed the ribbon cable on the back of this laser. That's just two little standoff screws that goes in the back. And I'm ready to solder the ribbon cable to the actual resonator block here. There's a couple of connections I'll need to make. Let me go and show you those real quick. So we got the two thermistors, and they get connected to these connections right here. So flip it over. You can see the positive and negative there. That's for the thermistor for the pump laser diode. And then this positive and negative right here is for the thermistor for the actual resonator. And if you take a look inside, they have a common connection right here. I've had to bypass the ribbon cable because the vias got pulled out. I also had to replace the thermistor in the resonator block for the pump laser diode temperature. That's what these red wires are right here. And then we have the thermistor wires that come out from the crystal. I have to fix that extension. And these wires right here are for the TEC that the crystal sits on. So a couple of things. Oh yeah, and the TEC, of course, for the pump laser diode. So let's go ahead and start soldering the ribbon cable onto the resonator. I'm going to start with the TEC wires for the pump, which are the big red and black ones. Soldering iron. Hopefully these will all go together pretty quick. Alright, so the pump laser diode TEC gets connected to these little ribbon connections here on the back. Just like that. The next wires I am going to connect are the pump laser diode TEC, the thermistor wires. So carefully grab those. and I gotta put them in those two little holes right there. Okay, now I should be able to fold that up and set this all in. I gotta find a screw, hopefully, that is short enough for that screw hole. Let's see what I have in my Protera parts. Okay, and I wouldn't advise putting a screw in before you put the crystal thermistor wires in, but at this point, since I have to extend them, I'm just going to run a wire over to the other side of the ribbon and just solder it that way. So I won't be doing that from the other side of the ribbon cable. Alright, let's fix this now. And this plastic coated wire is a nightmare. Doesn't melt or do anything really easily. And there's not much of it. See if we can get some of that off. But the best way to deal with this wire is to burn it off, fortunately. Okay, that's both thermistors connected. We can go ahead and double check that with the multimeter. They should both read about 10K. That one looks good. That one looks good. Okay, very good. Now, there's only two more things to connect, and that is the pump laser diode and the crystal TEC. Let's go with the pump laser diode first. We have anode and cathode. The cathode on mine is actually this little blue wire here that I gotta be very careful with. Oh. Alright, I gotta make that cathode connection down on the ribbon cable by by this J7 right here. Cabling just makes it. Looks clear, and then positive. So I made a little positive tab earlier, and that'll just screw on the top like this. Don't need wizard hair right now. We're dealing with mortal terms. Just like that. And then the anode, the positive connection, which is this entire copper block, gets connected to that ring right there. Alright, now there's only one major last thing to connect, and that is these two wires that go to the TEC that the crystal on the inside of the resonator sits on. And there's a 50% chance that I hooked this up correctly. Now, I noticed that on the ribbon cables too, you'll see on this as well, it looks like that the ends of the ribbon were cut. And so what I did is I scraped away some of the ribbon and I put 2 solder contacts on there and I traced the wires, and the wires actually are for the crystal TEC. So instead of soldering onto the pins on the back like one of them had them, I'm just going to use those 2 tabs. It's easier to access. So we have a 50-50 chance of this being the right way. Okay, that should be it. This should be a fully functional Protera laser module, plus or minus some bits. I think, yeah, no, it looks complete, except for the collimating lens on the front. I also, get off. Oh, a little bit of epoxy. That's nice. That'll buff right out. We're gonna ignore that for now. I also had to make a little aluminum shim which sits underneath. I don't know if you can tell, but there's actually a slight height difference now, and that is because the thickness of the thermoelectric cooler that I put in is actually a little higher, a little thicker, and so I need to move the optical pickup up a little bit as well. Otherwise the laser beam ends up clipping the top instead of going through the center. So I'll address that later, but as you can see, that just slides in nicely like that. Bada bing, bada boom. But let's see if this works. So, homemade driver. I'll connect this to power, and what we'll do is we'll see if there's any laser emission, and then check to make sure that the TECs are in the right configuration. I'm almost certain the pump diode TEC is, but as I said, I don't know about the resonator because it's not marked. Okay, so if this is all properly wired, which I do believe it is, we should see both of these LEDs blink. If, for example, I see the crystal LED like stay on and it doesn't start to oscillate, there's a problem with that. Either it's not cooling or it's wired backwards. That's the main thing I'm going to be watching. So let's dial some voltage into it. Turn off the light. And we have some laser light. Very good. The crystal LED is not doing anything, so I'm gonna have to turn that on. My kingdom for a flat plate of screwdrivers. Right, that should work. Is the resonator cooling? Yep, it should be. That looks good. Back off the resonator, the pump diode temperature. I'm gonna set the resonator TEC. We'll see if that oscillates as it should. Okay, wow. This is not working. Right. Try another tool. See, I can either get blinding bright shop light, strobe mode, or I can't see anything. Nope. The TEC for the crystal is backwards. You see how that light's not blinking? It should be. But it ain't. So, let's address that. Yes? What are you doing? What's going on? It looks fine. Why are you not doing your job? I have no idea. Next laser, well, we'll deal with that a little bit. I want to see green photons, and I have my own agendas. Okay, so this one actually is going to go together real quick, because everything is already right by the ribbon cable. Same basic connections as we had before, so I'll point those out to you real quick. So, over here we have the laser diode. So that's anode and that's cathode, and I gotta put the cathode back on here after I carefully save that wire. We have these two connections coming out, and that is for the thermistor for the crystal on the inside. And then we have the other thermistor wires coming right here. So that's for the pump laser diode thermistor that's sitting in the back. And all of that gets connected to these right here. So crystal thermistor, and then pump laser diode thermistor plus and negative. Now it doesn't matter for the thermistors which one you connect to which. They're not really polarized from what I know. And then down here we have the connections for the crystal TEC. So you see X. X stands for like cross, like crystal. So we're gonna go ahead and connect everything up, which should be actually really quick in this case compared to the 488. We will need to raise this eventually, but once again, just making sure that everything inside works as it needs to before the fine details. So that. So first I'm going to connect the laser diode cathode, as I said, which is this way right here. Carefully fold that over. Ah, getting a head cramp. Did you know that most of the laser work that I do is off camera? So that way I don't have a head that's completely locked sideways. Completely locked sideways, so I always look like a curious doggo. Curious doggo. Finally. Alright, so I put these blue wires on there to extend the connections up from the connections that were originally soldered there. So I gotta clip these and make those connections. Okay, I'm gonna test it before I pull the heat shrink over those, just to make sure that the TEC is in the right polarity. Take this, that is the positive wire, and goes onto the resonator block. Huh, wow. We'll borrow the screw from this one for the time being. What? Okay. Thermistor wires. Oh, those little tiny wires go on so much easier when you have stereoscopic vision on your side. But they're all connected, so it's time to test everything. The only thing I didn't check over was these wires here for the pump laser diode TEC. So I have no idea whether the polarity is correct on those, but we're going to find out. And one of the last things I'm going to have to do is also position the optical pickup a little higher in this laser. All right, power. Yeah, this one should be all set for the most part. Goodbye. On. That thing. Well, that's comforting. Okay, well, looks like I have to look over some problems because I don't know what's going on now. I've done some wire wrangling and I believe everything is now solved, at least electrically. One of the things that was throwing me through a loop was this section right here where the crystal TEC gets connected to. So on that ribbon cable section where it was cut off, I thought that the two traces right next to one another were the connections for the TEC. I was wrong. It's actually that connection on that side and then this connection on this side. Don't know what this connection is supposed to go to, but on one of the laser heads that I was working on, where the ribbon was cut, those two sides were still making contact. So I thought that was one trace, and nope, it's not. So I went and fixed that, and now the crystal TEC works in this laser. Everything matches with the one that I put together. So this was my follow along example unit. So that way I knew how to wire all these, which makes 3 lasers. And I also have this. All it needs is a collimating lens, but it looks fully put together and should make a good display piece. So let's go ahead and actually connect that up, see what we can get out of it. Made in the USA, fixed in the USA. Okay, let's turn on a power supply. I am going to tune the temperatures in a little bit, see what kind of output we get out of this laser real quick. And since you know exactly what the tuning process looks like with those 2 potentiometers, I'll probably just fast forward through this process. But here we go. Turning off the light. Turning on the laser. We get a little blue output. Throw one of the collimating lenses in the front. Or not. That's cool too. Yeah. Short out the LED. I don't care. And here we go. So here's our output. Let's fiddle with some temperatures. let's warm up the laser a little bit. These are basic TEC controllers, so I can only configure them one way, and it's actually pretty cool today, so we'll let that warm up. I might need to reconfigure my TEC controller here. Oh yeah. Well, it's getting pretty bright. That's actually getting really bright now. Wow. Yeah, I'd say there's a lot of hope in that laser head. Very good. Very good. Let's try the other laser head now. Yeah, that's putting out some nice power. Oh, they went the color limiting lens. Not bad. Not bad. You can even see it with my shop light. Pretty nice. Let's try the last 488 nanometer laser. These lasers are really only rated for 5 to 15 milliwatts, and I'd say we're getting at least 5 milliwatts out of this unit, so alright, and last but not least, I think the green. Okay, the green is still a little weak, but the TECs and thermistors and everything else seem to be working fine. So I think all the laser heads are about as good as they're going to get. Now, I do have configurable TEC drivers that I put together, and I could always hook the laser heads up to those and get a little bit more range. But at this point, I do have a Protera laser driver on the way, and I'm going to wait till that arrives, and we're going to hook the lasers up to the laser driver, because it should be an auto tuning one, and hopefully we can see what these lasers do on an appropriate driver. Turns out I'm a person with limited willpower, and that led me to reconfigure the thermoelectric cooler control portion of my laser driver here. Now, I really want to see what this 532 nanometer Protera laser will do, and I don't have another 1064 nanometer pump diode for this particular style of laser. So, I just want to see what it's capable of before I possibly cook the pump diode on that auto tuning laser driver. So, let's see what we get. On. Now flip this over so you can see the 2 activity LEDs for the thermoelectric coolers here, and speed up the video until it warms up. Now mind you, this is supposed to be a 5 milliwatt laser. Not sure how much I'm getting, but we have green photons. Up to this point, I've been pretty successful at trying to get these Protera lasers to work again. However, I believe I've hit the moment of expectation versus reality, and quite honestly, I don't know where to take it from here, but I'm going to try and make the best of it. Now, in discussing these lasers with a few friends, I've also talked to my friend Philip, and he said he had some things he could send my way to hopefully help with this project. Namely, a cable, and a driver, and I even managed to get an outer shell for one of the units so we can get it looking as nice as possible. If you're interested in used laser stuff, go ahead and check out his eBay page. I'll list that down below in the description, as well as a couple of other individuals who sell some interesting used laser bits. Now, expectation versus reality. The bad news is I could not get this driver to work with any of the lasers. And in fact, I couldn't even get this driver to work with any of the lasers. Now, I believe that the problem is the TECs that I used to replace the TECs inside of the Protera lasers had too low of an on resistance, and they're very high current compared to the ones that were in there. So I'm betting that's an issue. I also think that inside of the laser drivers, there's some sort of watchdog part of the program that measures the temperature slope, and I think that the TECs aren't responding in the way that the programming wants, and therefore they're not starting up. I tried to check to see if the TECs were in reverse bias as far as the polarity, and I made this little adapter to go between the laser and the cable, and I could just easily flip the TEC polarity here for the crystal and the pump laser diode. However, that yielded no success, so I'm not exactly where to go on that. I also noticed too that on the pictures that my friend had of his working unit, there was something here in the D1 position. Did I say D1? No, D3 position. And I'm not sure if there's something that needs to go in there or not, but I don't think so, because if I remember right, one of these actually, no, it's not that one. One of these has glue in the hole. Yeah, so let's take a look in there. You can see that little hole is covered in glue right there in the corner. So, and that's where that part mounted. So I'm not sure what that does, but long story short, I couldn't get any of the drivers to work. So I'm going to open up the drivers and I'm going to show you what's inside of them. And as I do so, I'm going to try to explain a little bit of the backstory behind these Protera units. Hopefully my ADHD brain taking these drivers apart doesn't get too distracting. Now, when these things were made, they were notoriously unstable. One of the people that my friend spoke to said that they would change because of things like humidity and temperature and other evil forces in their environment. But I really do think that it was a thermoelectric cooler feedback problem, and I think that's because of thermal oscillations and so on and so forth. And I also do think that the TECs broke in a lot of these. Do I need that? No, I don't. Okay, cool. And I also think a lot of the thermoelectric coolers broke well before anything else in the laser did, which would also explain a lot of the problems in operating in different environments. It just couldn't properly keep the laser at the right temperature. I don't think that things like humidity and barometric pressure would really affect these lasers all too much. It's been said that if you had one of these lasers in a room full of people with PhDs and $100,000 worth of equipment, you could get any of these running, However, giving it to a $2 microcontroller, forget it. And that right there would be the $2 microcontroller, I believe. Digital bits aren't my forte. No, as an analog device, it can't be the microcontroller. One of these is a microcontroller. I mean, that has to be it, right? So many things I don't know, but I know the analog bits and the power electronics, so we can take a look at that. Alright, so we got the power input here, and I'll let you know right now if you have one of these. Both of these are DC, negative, and then this is positive 5 volts. So here's your ground, 0 volts, and here's your positive 5 volts. This takes quite a bit of current, so I'd say use like a 3 amp power supply if you have one of these. And here is the data interface and also the interlock. So that's on there, that's not a problem. Yeah, I really do believe this is a microcontroller, even though it says analog devices. There's a clock crystal on there, and we probably got a couple of like serial drivers for communication too. Let's go over to here. In that section, we have all the DC to DC power management and control for the thermoelectric coolers. So I've got this inductor right here, this inductor right here, and it's probably for providing the voltage rails and everything for between the TECs. Go ahead and see what that part number is. We can at least look it up later. There you go. See what that is. But that's all in this section. And we have these 2 chips right here. And I believe that those are NPN, PNP, or N-channel, P-channel MOSFET pairs. And probably driving an H-bridge output to the pump laser diode. I'd explain those heavy tracks, so you can see where those traces go, right where the DC to DC converter inductor is. A couple of other heavy tracks here. So those would go out to the thermoelectric cooler. Yep. Now what's interesting is it looks like there's only one H-bridge. So I'm believing that the actual copper block for the pump laser diode, this would be the only thing that would need an H-bridge to drive the TEC, because once the temperature is set on the copper block, whether it's warmer or cooler relative to the ambient environment, the crystal would only need to be warmer or cooler from that set point. So I doubt that TEC for the second harmonic generation crystal, frequency doubling crystal, needs a H-bridge. Of course, there might be one on here. It might be smaller. Yeah. For driving the laser diode, we have the output transistor here. We got a current shunt resistor, 1 ohm. And follow that over here. Here's your negative rail. And probably got an op amp around here somewhere for doing the comparing. We'll follow that right at. That's the feedback from that shunt resistor right down here, going to this via, going to that mess of resistors. So one of these bound to be an operational amplifier. But yeah. So H-bridge for the TEC for the pump laser diode. 2 DC to DC converters, 1 driving the H-bridge here. This one's probably just driving the TEC in one polarity for the crystal. Final output transistor that does the constant current control for the pumping laser diode, current shunt resistor, feedback from that, and then the network here for the operational amplifier and like feedback from the photosensor, which all goes to the microcontroller. So pretty small unit. Not a lot of linear components on here, except for that final transistor. Getting into the NovaLux story a little bit more. So, yeah, if it wasn't for the failure of the Proteras. NovaLux might still be around. I think that they're no longer their own company. If I remember right, they were bought out by Nexcel, N-E-C-S-E-L, and they make lasers that are very similar to how the Proteras work. So they have a vertical cavity surface emitting laser on the inside, and they go through a periodically pulled crystal, same way that these do, except they put out a lot more power in a much smaller package. And I'll tell you, I'd love to get my hands on one of those and maybe do a little bit of comparing between those and their progenitor. Let's see, do I need to take that out? Nope. Looks like I just need to take the power ring out. Where's the right tool? There it is. It's at least the more right tool. But yeah, these are notoriously unstable lasers. But if you get one that works, some of them can do single longitudinal mode, SLM, good for holography from what I hear. And in general, if you're looking for a laser just to tinker around with and try to get working on your own, these aren't too bad of a laser to work with. They're very forgiving, and it looks like for the most part you have a good chance of the entire laser, the parts being good. The failure mode looks to be the thermoelectric cooler, and replacing that isn't a big deal. Pull this out. A little bit how you doing? Kind of clip in there. Alright, let's take a look at this board. So the top board here looks to be for doing the constant current and the optical feedback portion for the control of the pump laser diode and stability. And I think that because we have some calibration potentiometers up here, and that's close to this right here, which I believe is a MOSFET or an NPN transistor, and that's probably doing the regulation of the current for the pump laser diode on the inside. Looks like this board comes off. I'll go ahead and do that. Yep. So probably for like constant current and linearity, though that's just a guess. Not exactly sure what that switch is, but I'm not gonna mess with it. Alright, just once. I'll mess with it once. Okay, I can put that down. That's the input filtering capacitor for smoothing DC input, looks like. And this takes 5 volts. The outside is negative, the inside is positive. Got the switch for controlling the laser, so this way would be TEC and laser on, sensor is off, and then this way would be just for the thermoelectric coolers. That way you're not running the laser, but you can keep it stable. Oh, let's see. Some decently large, looks like polyvinyl, the plastic film caps, probably to smooth out some of the ripple coming off from various components going to these right here. Unlike the DC to DC converters that were on the actual Protera board here, they've gone with a different solution. So instead of using a DC to DC converter to supply the exact current or voltage needed for those TECs, they're actually using these analog modules here. Not analog, but linear. And well, you know they're linear when you plug in the low resistance TEC, and one of them gets really warm. So this one is the one that gets really warm, and obviously the one that does the pump laser diode regulation. Once again, no problem with it. The pump diode does cool down or warm up, but I get no activation of the laser. This one doesn't get nearly as warm, which means that it's controlling the actual crystal temperature on the inside of the resonator. These just, they're little modules. You can plug in a thermistor and run them. These haven't been made in a while from what I remember, but if you can find them. They're actually really stable, and people who are interested in doing holography like these because they're really good at maintaining that ideal temperature to a fairly small degree. Low hysteresis. Now we got the adjustment potentiometers for each one of those temperatures. So, almost a completely linear solution. Is there a digital controller on here at all? I don't think so. I think this contains absolutely no smart thinking bits at all, but I could be wrong. Yeah. No. A completely linear dumb solution and a DC to DC switching linear hybrid solution. Neither one of them works. So at this point, let's continue discussing my solution. Now, I don't have a PhD, nor do I know the entire fiscal net worth of my test equipment, but what I do know are some simple circuits that'll help you get these and several other variants of semiconductor-based lasers operating. Except for this one, which sadly gave up the ghost during tuning. It just got dim and I tried to fix it and no dice. But I do have some pictures of the resonator running, and I'll put those pictures up after this portion of the video. In the latest Nova 50 video I talked about two circuits, which is the constant current driver that I'm using right here, and then the simple TEC controller. Now, the difference between the TEC controller I used in that video and the TEC controller here is that this also includes a 555 timer, which gives me a PWM duty cycle that allows me to control the total average output power going to the TEC that this driver controls. And that allows me to minimize thermal oscillations as described in that video without the use of resistors. I do have resistors here for basic current limiting, but it's not needed as much. The circuit I want to discuss in this video is right here, and it's a thermoelectric cooler driver that has the added benefit of a full H-bridge output. So if the part is too cold, it can warm it, and vice versa. If it's too warm, it can cool it. Now, this is a very simple circuit. Here's the diagram. So it's based off of two ICs, the LM358, which is a dual operational amplifier package, and the LB1641, which is a small motor driving H-bridge IC. Let's talk about the LM358 section here. I've got my power input wires on pin 8 and pin 4, which is negative and positive. And then on the LM358, we have a set of inputs for each operational amplifier in here, which are the inverting and non-inverting. On the inverting and non-inverting inputs, I have them crisscross. So on one amplifier, I have the non-inverting connected to the inverting, and then vice versa, I have the non-inverting connected to the inverting. And those two crisscross sections of inputs are connected to a pair of voltage dividers. The two voltage dividers are very simple. We have a 10K potentiometer right here, and that's in series with a 200K resistor here. And the reason why I have a 200K resistor here is because the LM358 uses very small signals, and this is just to limit the current voltage going into that input. Over here, I have a 10K NTC thermistor, and I have a 12K resistor here, and that is basically the equivalent to this 10K potentiometer here when this side is running. And once again, I have a 200K limiting resistor here for the same reason as I have this one, just to limit the current voltage going to those sets of inputs. So how this circuit works is if the NTC is warmer, it'll be higher than the other signal, and it'll turn on its own output on that operational amplifier. But if this is cooler, it's going to be lower than this, and then it's going to turn on the other output of the other operational amplifier. And those two outputs are these brown wires right here. Now with the LM358 there is a little bit of hysteresis, and that means that both outputs can be latched on at the same time. And if you have any kind of familiarity with H-bridges, this is a no-no. You don't want two positive outputs going to your H-bridge, otherwise you fry transistors. However, the LB1641 is smart, and it will not draw current, send that power through the H-bridge if both of these are high. Over here I've got two 10K resistors, and that's just to make sure that the outputs of the 358 are properly pulled down when they're supposed to be off. And for the LB1641, there's some simple passive components that need to be added. So between pin 1 and pin 4, I've got a signal dial. This is a 4148 right here with the cathode going towards pin 1. A 10 nanofarad capacitor here between pin 3 and I believe that's pin 9. My input for the positive is over here to this pin, and then I got my negative going over here to pin 1. On my board, I have a current limiting resistor as like 2 ohms going into here just to make sure I don't cook this by overcurrent, just by accident. And then I have my output wires in green coming from the LB1641, which would go normally to a motor, but in this case, it's going to my thermal electric cooler. Let's take a look at the board. Okay, so in this section right here, I have my 358, and you can kind of see how those inputs are crossed. And then over here, my 2 voltage dividers, one with the potentiometer and then the other one with the NTC thermistor. So right here is my thermistor inputs. On the diagram that I drew, I don't have anything for amplifying the output of the LM358 to drive the LB1641. On this board, I just have 2 driving totems, like you would for driving a MOSFET, which are comprised of smaller MOSFETs. So these are 2 N-channel, and these are 2 P-channel. You can probably also use a dual-channel gate drive IC, although I have the feeling that the way I drew the circuit will work just fine, and you don't even need this. You can see my 2 outputs here, so there's an output coming from the LM358, and you see these 2 wires here coming off my totem. You could probably just directly connect these 2 outputs from the LM358 to the inputs of the LB1641 and be perfectly fine. Wouldn't need it at all. If you're curious as to the other boards, here's the one with the 5555 timer. Kind of hard to see. And then there's the top side. I'm going to give you a moment just to investigate how that board works in detail. I have a couple of LEDs here. The green is just for general output from the H-bridge. Where's that power? No, that's just power. And then I have a blue and red LED, and these are just in reverse bias. So if the polarity is one way coming off the H-bridge driver, it'll be one color. And then if it's the other polarity, it'll be the other. But there's not really much to it. Of course, add in some smoothing capacitors on your power input just to make sure you get a nice clean signal. But pretty easy board. Let's hook up one of these Protera Laser units just so I get better control and minimize the interference between everything here. I have the TEC driver for the pump laser diode for the copper block on an ATX power supply, and then these 2 I have on my regulated DC power supply. That way they don't chatter too much. I'm gonna plug in everything and we'll hook up a laser head. Let's hook up the collimated one. Okay, all the wires look good. Can you see that? First, I'm going to turn on the power supply for the TEC, or the pump laser diode. And when this is done properly warming up the laser, these actually do like to run warm, about 30 to 36 degrees Celsius. You'll see that this blue LED will turn off, and this white LED here will also turn off, and then it'll start oscillating depending on the requirements of that thermal load. I'm going to turn on the power supply for these, and that might cut down the quality of the audio, but fans are important. I'm going to turn off the light. We can watch the output. Mind you, I do not have the temperature for the crystal tuned on this laser head, so we're going to have to go ahead and tune this after the pump laser diode is at the correct temperature. Okay, the pump laser diode is now up to the proper temperature. We can tell because this driver is now gone into oscillating. And all I have to do is tune the correct temperature. I don't know if you can kind of see it or not, but there's this little blue light lighting up. And when it goes red, it's warming. So I'm going to go ahead and tune in that temperature. Well, that's pretty good for some primitive laser driving now, isn't it? Take a look. Fine camera action. So you can see that this LED lights up red because it's warming the crystal ever so slightly at certain points. And then same thing here, it's warming the pump laser diode at a certain point. So both these are now stable in temperature for the most part. And we have a nice stable output here. You can see it clear as day with my bright shop lights on. That's some nice laser right there. Doesn't get much more simpler than that, does it? Temperature plays a huge role in these types of lasers, much like it does in GPSS and OPSL systems. As the pump diode and second harmonic crystal change in temperature, multiple transverse or longitudinal modes can often be generated. These can be clearly seen in the uncollimated output of this Protera laser. These lasers were originally manufactured 20 years ago
and it's impressive how well they still seem to perform once operating. The biggest issue seen in this video appeared to be the pump laser diode TEC, and while the blame for unstable performance may have been evil, unknown external forces, it really feels like it was really a possible demise simply caused by poor shipping and handling over time. The NovaLux Protera Lasers have decently nice beam characteristics when they choose to. When aligned correctly and driven with proper temperature stabilization, they produce very thin, low divergence, round Gaussian output. Thanks to the outer shell that was sent to me, I was able to get one of each style as close to fully assembled as possible. With proper care, there is little doubt that they are probably going to work in the year 2044. Though they carry with them a reputation of instability, they are still worthy of redemption, and if you find a NovaLux Protera laser with both TECs working, there is a good chance that it will work for years to come. The Protera lasers also have a very low line width, and I've heard some are single longitudinal mode, abbreviated as SLM. These might be relatively good lasers for holography. When a material containing a perforated hole pattern is placed into the beam, nice interference patterns can be generated as an output. Making stable lasers is a tricky task and requires knowledge in many fields, multiple types of materials, and oftentimes specialized electronic control systems, and NovaLux is not the only company to have produced a questionable line of lasers. The Protera wasn't a dead end in laser technology. It lives on still and evolved into Nextel lasers. Thank you to all who made this video possible. I hope you enjoyed, and as always, stay tuned for more.